Alright, so I have my T, I have practice exam A, and I have my equation sheet, which I'll share with you guys. It's only 2 pages long. So let's get started. Alright, so first question we have here says the figure below shows the concentration of dye molecules in a tube as a function of position along the tube. Sketch the concentration of dye molecules a short time later. Okay, so this is talking about concentration, and we know that we started talking about concentration when we talked about Brownian motion and diffusion. So if we look at Fick's laws of diffusion, Fick's second law says that the bumps are going to get smoothed out. So if the concentration looks like a frown, the concentration is going to decrease at that point, and if it looks like a smile or a cup, it's going to increase at that point. So the question here really is, how do you figure out whether it's up like a cup or down like a frown? Well, you look at a point on the graph. So here, it's pretty obvious that this is curving down like a frown. So the concentration here is going to decrease. And it's pretty clear that this is like part of a smile. So the concentration there will increase. And if you look here, it's like this case. So it's going to go down there as well. What about this point? So is that part of a frown or is it part of a smile? So just because there's no minimum there doesn't mean it's not part of one of these. So here, this is curving. It looks like it could be part of a smile, right? Like if you kept going like that, it would be part of a smile. So this part's going to go up a little bit. And the same thing's going to happen over here. If you find a point where the slope is like straight, there's going to be no change. So this point isn't going to change. That point's not going to change. That point's not going to change. And that one's not going to change. So if you look a little bit time t later, it's going to look something like this. This goes up a little, down a little, and up a little. It's going to look something like that. So this is the only thing we can really do with Fick's second law. So you can probably bet that there's going to be a question similar to this on the actual final exam. Okay, let's look at problem 2. So you've actually seen problem 2 before on a previous exam. So this says Marvin pushes a box across the lecture bench with coefficient of friction mu from left to right. So he takes the box, moves it over here. Then he pushes it back to where it started by pushing it from the right to the left. The box stops and starts at rest. Okay, so this is the same as the Piglet question from the last exam, I think. So it says the work done on the box by Marvin is positive, negative, or 0. So if we look at our equation sheet, let's see, and let's look at the work section. Where's work? Here it is. So the work done by a force F is the force F dotted with the path that the object takes. So the sign of work depends on the dot product of those two vectors. So if you think back to dot products, the work is the force dotted with the displacement, delta R. So if the force and the little piece of the displacement vector is delta R. If they're in the same direction, it'll give you a positive work. If they're opposite, you're going to get a negative work. And you can calculate it for any angle between the two vectors, because if you recall, the dot product is F delta R cosine of the angle between the two vectors. So whenever the angle between the two vectors is less than 90 degrees, you're going to get a positive work. So Marvin is always pushing in the same direction as the displacement of the box at that point in time. So that means that the work that Marvin does on the box has to be positive. Now, how about the net work done on the box by all the forces? Well, there's a key theorem called the work kinetic energy theorem that says that the net work done on an object changes that object's kinetic energy. So the net work equals delta KE. Okay, so we want to know the net work. Do we know the change in kinetic energy for the box? Yes, we know that the box stops and starts at rest. So that means that the kinetic energy, which is given by 1/2 mv squared, kinetic energy is 1/2 mv squared. If it stops at rest, that means V is 0 for both the initial and final kinetic energies, which means that the total change in kinetic energy is 0. So that tells us the net work done on the box is also 0. Now, how about the work done on the box by the kinetic friction force? Well, as the box moves, the friction force always points in the direction opposite the motion. So if the displacement vector is in this direction, on its way over, the friction force is pointing in the opposite direction to the motion. And then when Marvin pushes the box back to the starting point, the displacement is this way, and the friction force is again acting opposite to that motion. So this is always going to give us a negative dot product because this angle is 180 degrees. So this will be negative. And indeed, if you add up the work done by Marvin and the work done by kinetic friction, which are the only two forces doing work on the box, that will sum to 0 net work.